welcome back to the Explainer. Today, we're going to do something a little different. We are taking apart a power drill. Not to fix it, nope, but to find the hidden mechanical solar system that's tucked away inside. It's an amazing system of gears that turns a tiny motor's high-pitched whine into some serious, unstoppable force. And you know what? It all comes down to some surprisingly simple math. I mean, you've probably wondered about this, right? It feels almost like magic. You hear that high-pitched whirring sound from a tiny motor, but somehow it translates into enough raw power to drive a screw straight into a piece of solid wood. Well, the secret isn't magic. It's just a really beautiful piece of engineering that turns high speed into incredible torque, and it all boils down to some elegant algebra.
Okay, let's just dive right in. And seriously, if you ever have a drill that breaks, don't just throw it away. Take it apart. It's a fantastic experience, because inside you're going to find its secret weapon, the planetary gear system.
And this is what you'll find. It's not just one or two simple gears clicking together. No, it's this intricate, beautiful, interlocking system. This right here is a planetary gear set, and what's so amazing is how compact, how efficient, and just how incredibly powerful it is.
Now, the best way to wrap your head around this whole thing is to think of it like a miniature solar system. It's actually a perfect analogy, and the names of the parts themselves give you the perfect mental model for how it all works together.
So right at the very heart of the system, we have what's called the sun gear. This little guy is connected directly to the motor's shaft, which means it's spinning like crazy, carrying all of that initial high speed but pretty low torque energy.
And orbiting our sun gear are, well, you guessed it, the planet gears. Now, these are the real heroes of the story. They're the key to this whole mechanical puzzle because they do two things at once. They spin on their own little axes, but at the exact same time, they're revolving as a group around that central sun gear.
So what keeps these planets from just flying off into space? Well, that's the ring gear. Think of it as a fixed outer wall with teeth on the inside. It doesn't move. So as the planets roll along the inside of this ring, they turn the plate they're all attached to. That plate is called the carrier, and that is our output. It's what connects to your drill bit, and it turns slowly, but with a whole lot of force. Okay, so we've got our mechanical solar system all laid out, but how exactly does it turn that fast, weak spin from the motor into a slow, powerful turn at the drill bit? Well, the answer isn't buried in some complex physics textbook. It's right there in the algebra of motion.
All right, I see the equations, you see the equations. Don't let them intimidate you. We're just going to walk through the big ideas here. Our goal is to find something called the transmission ratio. That's just a fancy way of asking how much slower is the output than the input. Or, to put it another way, for every one time our slow, powerful carrier turns around, how many times did this super-fast sun gear have to spin? That's the number we're hunting for.
You know, the math here starts with something you can just see with your own eyes. It's a simple physical fact. Look at that first equation. All it's really saying is the parts have to fit together. The total size of the outer ring has to be the size of the sun gear in the middle, plus the two planet gears on either side. It's just simple geometry.
Okay, now for the really brilliant part. The second equation. That's where the magic happens. Remember how we said that outer ring gear is stationary? It's not moving? So as a planet gear rolls along it, the point on the tooth that's touching the ring has a speed of 0. But the center of that planet gear is moving forward. And because of that, the opposite side of the gear, the side that's touching the fast-moving sun gear, well, it has to be moving at twice the speed of the center. That single insight right there is the key to this whole thing.
So what's so cool is that after you work through those relationships, all the complex stuff, the radii, the speeds, it all just cancels out, and you're left with this incredibly simple and beautiful formula. The transmission ratio is just 1 plus the number of teeth on the ring gear divided by the number of teeth on the sun gear. That's it. I mean, that is the magic right there. The size of those planet gears, which seemed so important, they don't even show up in the final equation. You can figure out the exact power increase of the entire system just by counting the teeth on 2 of the gears. How cool is that?
So a single one of these planetary stages gives you a really nice boost in torque. But what if that's not enough? What happens if you take the slow, powerful output from one stage and you use it as the input for a second stage? Well, this is where things get truly mind-bending.
Let's put some real numbers to it. Let's say one of these gear sets has a 4-to-1 ratio. So if you chain 12 of them together, back to back to back, what do you get? Now, the answer isn't 4 times 12. The really crucial thing to get here is that the gear ratios don't just add up, they multiply.
And this is what that looks like. It's a 3D printed 12-stage planetary gearbox. Every single one of those colorful segments is a complete gear system, and each one takes the output from the one before it and multiplies its power all over again.
And the math on this little sticky note, wow, it just shows you the incredible, almost unbelievable power of exponential growth. You take the ratio of a single stage, in this case about 3.6 to 1, and you raise it to the power of the number of stages you have. So 3.6 to the power of 12.
And the result is a final gear ratio of over 5.3 million to 1. Just let that sink in for a minute. For that final gear on the end to make one single rotation, the tiny little input shaft at the beginning would have to spin more than 5.3 million times. You've basically created a device that turns incredibly slowly, but with an almost unstoppable amount of force.
Okay, so let's bring this all back. Let's get out of the land of 3D prints and back to that tool you might have sitting in your own toolbox.
The next time you pick up a power drill, just remember what's happening inside when you pull that trigger. You're not just using a tool. You are wielding the power of a tiny mechanical solar system. You are wielding the power of exponential growth, and it is all governed by that one beautifully elegant equation.
And that really is the key takeaway here. Math isn't just something you find in a textbook. It's a hidden wonderland of mechanics and motion, and it is quietly working inside the objects we use every single day. The only question is, where are you going to find it next?